Okay, so in this video, I'm going to talk about conditional versus absolute convergence. I'm just going to do like a few examples. So we're going to look at a few series and we're going to determine whether they converge absolutely, converge conditionally, or if they diverge. So I have these 5 series that I'm going to cover in this example video. So let's start with the first one. So I've got -1 to the n plus 1 and then 3 times the square root of n plus 1 over the square root of n plus 2. All right, so the first thing that we want to do is we want to notice, so this is an alternating series, right? And so we can use the alternating series test to kind of help get this party started. So there are 3 conditions for the alternating series test. So an alternating series converges if all of the u sub n, so this is the non-alternating part of the series, if those are positive, they're eventually non-increasing, and then if the u sub n's go to 0 as n goes to infinity. So usually this first condition is the easiest to prove. The middle one is actually like it can be harder because you'll have to use derivatives. And then this one here is maybe the second easiest or second hardest, however you want to think about that. So this series is obviously positive, right? Because I'm putting all positive n's into it. So that will stay positive. So like I said, that one's usually the easiest one. The next thing though is let's go ahead and evaluate. So the limit as n approaches infinity of this whole thing. So what I want to do is, just to help me evaluate this, I'm going to divide the top and the bottom by the square root of n. So when I divide that in, since everything here is being multiplied together, I can just apply it to the part that I want, i.e. this part right here. So I just want to make sure I'm clear with the algebra in case you need to see it. So this is now going to become n plus 1 over n. So since this and this are both in square roots, we can just combine them into one mega square root. And then in this denominator, so this will be 1 plus 2 over the square root of n. And let's see, I'm running out of space here, but let's keep going. So this square root will turn into, so I'll break this into 2 separate fractions. So this becomes 1 plus 1 over n, and then 1 plus 2 over the square root of n. And now I can actually evaluate this no problem. So this part here is going to go to 0, and this whole thing is also going to go to 0. So what are we left with? We're left with now 3 times the square root of 1 over 1, and so this is just 3. Okay, so this did not go to 0, so this does not satisfy the alternating series test. But moreover, the other thing to notice here is that the nth term for divergence says that so a series diverges if the limit as n goes to infinity fails to exist or is different from 0. So our limit is different from 0, so therefore we get to say that this diverges. Okay, so let's keep going. So I've got the next one. So, okay, in this case, I've got same idea. We'll just go ahead and note, so these are all going to be positive. Clearly, you can pretty easily show the limit as n goes to infinity of 1 over n plus 3. This will end up equaling 0, so we're all good there. And then I think you can also like kind of actually tell for this one without needing to take a derivative that this is non-increasing. So if I just write out a few terms, so like the first term will be 1 over 4. The next term will be 1 over 5, the next term will be 1 over 6, the next term will be 1 over 7. So if I just start plugging in n's into this, so this is exactly what we're looking for. So I don't need a derivative to help me figure this particular one out. So some of these harder ones you're going to have to use a derivative for, but in this case I can pretty easily tell this series is non-increasing, which is this condition here. So everything has to eventually be non-increasing. So it's always non-increasing. Okay, so by the alternating series test, check, check, check. I've fulfilled my 3 conditions. So that means that the series converges. Now, I want to be able to be a little stronger in this, and I want to know, does this converge conditionally or absolutely? And the idea of converging absolutely would be that I would take the absolute value of this entire series, which if I take the absolute value of this, that just kind of nulls out this part, right? And so just notice this is really just the harmonic series in disguise. And the harmonic series, we know, always diverges. When it's just the classic harmonic series. Now, the alternating harmonic series does converge. So this means it does not converge. I'll just write ABS, absolutely. So if it doesn't converge absolutely, then we say the series converges conditionally. So that's the difference between the two. So if you know that it converges by the alternating series test, you're going to want to think through, does it also converge absolutely if you take the absolute value of it? Okay, so moving on to our next one. So now I've got -1 to the n plus 1 to the, and then the nth root of 13. So, okay, this is all going to be positive again. If I take the limit as n goes to infinity of, I'll rewrite this as, how about 13 to the 1 over n. Okay, so this is where knowing a common limit, so these are like on the list of common limits that I've given out. So this is just something that we know. So it doesn't matter what number I put here as long as it's greater than 0. So in this case, I've replaced my x with 13. So x has to be greater than 0. So this is going to equal 1. And so that's going to violate our alternating series test, right? So we have that the series itself is not going to 0. It's going to 1. And then once again, if we go to the nth term test for divergence, since the limit is different from 0, that means that the series diverges. So I know now this diverges, and so I'm done. So nth term test is pretty handy. Okay, onwards. So next I've got -2 to the n plus 1 over n plus 5 over n. Okay, so let's separate this actually into two pieces so that I can see this a little easier. So let's write this as -1 to the n plus 1 and then 2 to the n plus 1. So I can just break that up into two parts. And so this part here is the non-alternating piece of this, right? So all of this is clearly going to be positive because we're plugging in all positive numbers. And then the next part is what happens for the limit as n approaches infinity of 2 to the n plus 1 over n plus 5 to the nth. Okay, this gets maybe a little trickier. What we could do is we could divide, let's see, we could divide everything by 5 to the n. Now, before I do that, I actually want to break this up a little bit. So let's see. So I'm going to break this into 2 times 2 to the n over n plus 5n. Okay, and so then that just helps me when I do my division. Okay, so here I have 2 terms, so I divide both terms by 5 to the n. Here, these are all being multiplied, so this is just one term. So the way that I'm going to write this then, I'm going to have the limit as n approaches infinity of 2 times, let's call this 2 over 5 to the n, and then n over 5 to the n plus 1. Okay, so now, since this is a fraction less than 1, this is going to go to 0. This, we cannot state which way that's going to go. So let's see. If I take the limit as n approaches infinity of n over 5n, I can use L'Hopital's here. So let's see, what's that going to become? That's going to become the limit as n approaches infinity of 1 over the natural log of 5 times 5 to the n. Sorry, I'm kind of running out of space there. Okay, but this allows me to prove my point, so then this denominator is just going to keep growing. So this is also going to go to 0. A little difficult to prove that. Okay, let me get rid of all that. And now this leaves me with 2 times 0 over 0 plus 1. So this just equals 0. Cool. All of that work to show that this condition here, that the series goes to 0, is met. So we're all good there. Okay, and let me clear some space. Okay, and then this is also a case where I think just by looking at this, you can tell that this is non-increasing. So right, these are always going to get the top and the bottom are always going to grow, but it's always going to be a fraction that was smaller than the previous fraction. So you can technically tell from here that you've got non-increasing. You'd probably want to use a derivative to back that up. And I think this actually brings up an excellent point now. So the alternating series test, we can 100% use it here. I do need to show that these are clearly non-increasing. So to prove non-increasing, so this will be like, so if I just write this out, this becomes, if I plug in a few terms, so 2 squared over 1 plus 5. So that's going to be 4 over 6 for my first term. My next term is going to be 2 to the third over 2 plus 5 squared. So let's see, that's going to be 8 over 27. So when you look at this now, so if you're not sure what the decimal values are, so this goes 0.66, and then this is going to be 0.296, so on and so on. So we can see that this is decreasing. My point is, though, maybe it's like not always going to be obvious. I think in this case we can call it obvious. We can see that the terms are always going to kind of decrease like this. The bottom is going to continue to grow much faster than the top, so it's just going to continue to decrease. So I feel like you could use that. But my point is that sometimes this AST, so it can feel a little awkward. So you don't have to just use the AST. And by the way, the other thing with this is, okay, so I've proven that this series converges, but remember what this question was. The question was to prove whether we have conditional or absolute convergence. So the AST, the alternating series test, shows that we have conditional convergence for sure, but we still haven't solved the issue of absolute convergence. So now I need to take the absolute value of this, and I need to just determine if 2 to the n plus 1 over n plus 5 to the n, will this series by itself converge? And that's not something that the alternating series test does for us. So I've taken the absolute value. So now how would I just prove that this converges? Okay, well now I've got to use another test. And I can use any other test that I want, by the way. So I'm going to use the, let's compare. So we can use the comparison test here. So once again, so I'm going to rewrite this as 2 times 2 to the n over n plus 5 to the n. That just kind of helps make the exponents easier. And so now I can see a pretty clear thing to compare with. So I've got this 2 to the n and then 5 to the n. So, okay, let's build this up. So if I have n plus 5 to the n, that is certainly going to be greater than 5 to the n, right? Which then allows me to say that 1 over n plus 5 to the n is less than 1 over 5 to the n. I can't speak. Okay, so I can use this property here, and then I can multiply both of these by 2 to the n. So now I have 2 to the n over n plus 5 to the nth is going to be less than 2 to the n over 5 to the n. And then I can multiply these again by 2. Okay, so let me just show you the comparison test in case you're like, what is the comparison test? So if I have two series and I have this relationship set up here, so if so it depends on like which series you set up. But the way that this is going, so I've set up that my original series is a sub n and my comparison series is b sub n. And so I've set this up so that if b sub n converges, then a sub n converges. So going back to what I've written out so far, so let me make some space. So I've set up this comparison, and so I can say then this series here, so 2 times, this is, I'm going to rewrite this as 2 over 5 to the n. This actually converges because it's a geometric series. So this is a geometric series. So this is a fraction less than 1, so therefore this whole thing's going to converge. So if this converges, then by the direct comparison test, I'll show it to you one more time. You can pause if you want to read it over. Then the original series is going to converge. Okay, so what do I do with that? Now I've shown that I have both conditional and absolute convergence. So which one do I choose? We have absolute convergence. And I think there's a good lesson in here. So I want to remind you what the absolute convergence test says. So the absolute convergence test says if the absolute value of a series converges, then the series converges. So we started this, you know, because this is kind of a section on alternating series test, and it's like, oh, I want to use the alternating series test, but did I actually need to? So no, you actually didn't need to, because if it absolutely converges, then the series itself will converge. Now, the converse is not true, right? So if the series itself, so maybe I'll come back here. So the series itself might not converge absolutely, but it could converge conditionally. That's exactly what the deal is when you have our first example here, right? So the harmonic series does not converge. So this does not have absolute convergence. It only has conditional convergence. So if you're trying to decide how to spend your time most wisely, I would just try to test things absolutely first. Okay, so let's apply that lesson then to E. So instead of using now the AST right away, I'm just going to start by taking the absolute value of this, i.e. I'm going to ignore this, and I'm going to see, can I figure out if this converges? So inverse tangent over n squared plus 1. Well, this is kind of tricky, but one thing that I notice is that 1 over n squared plus 1, that is the derivative of inverse tangent. So this feels like a great time to use the integral test. So what I'm going to do is I'm going to integrate this situation. Actually, let's turn it all to x's. I like using x's when I integrate. X squared plus 1. Okay, so in this case, so my u will be inverse tangent of x, and my du will be 1 over x squared plus 1 dx. And then I will leave my bounds alone for a second. So let's just rewrite this as u du. And so then this will be, let's see, this will be 1/2 u squared. And so then I can change my limits of integration. So let's set up a limit as b goes to infinity of, let's see, this will be 1/2 inverse tangent of x, now from 1 to b. Okay, so here's now what I want to evaluate. So I'm going to have the limit as b approaches infinity of 1/2. I'll just factor the 1/2 out. Inverse tangent of b minus inverse tangent of 1. All right. Oops, and I forgot to square all of that. Let me square all of that. Okay, so now you do need to know something about like inverse tangent. So inverse tangent has an asymptote. So I know that this limit, let's see, this is going to turn into 1/2. So the asymptote is at pi over 2. And then inverse tangent of pi over 1 is pi over 4. So here's what I'm left with. And so this is going to simplify then to pi squared over 8 minus pi squared over 32. Okay, so what do I do with that? So remember, we were doing the integral test. So the entire purpose of the integral test is that if this integral converges, then this converges. And so since we found that yes, it converges to this, we can say that this converges, so that I don't have to worry about the alternating series test. Since this converges, then as an alternating series, it also converges. So we have absolute convergence. Okay, so hopefully that helped clear that up a little bit. So if that was helpful, please consider hitting the like button or subscribing to the channel, and I will talk to you guys next time.